Okay, so here's the code and solution. Let's run through it. So as you can see, we create a set which will keep track of the nodes that have already been visited. And we start with our first node. Okay, let's start at node 1. If root equals none, that's not the case. If root.right exists and the root.right value is in the self.scene, so the set, we return none, but it's not. So set so far equals self.scene.add root value, that's 1. Next, we recursively point the root to the right and then the left. Okay, so we have 2 branches now. So 3 is not none, and there are no values to the right of it, and it's not in the set anyway. So we just add it to the set. And on the left hand side, similarly, we have a root value, and we point it then to the right and check if this right value is in the set. It is. So we return none. 2 becomes none. So root.left returns none, and root.right equals 3. Therefore, we're left with 1, 3 as our final new tree. Okay, next example. Okay, let's look at the first example. So we start at root 8. If root is equal to none, not the case. If root.right and root.right value is in the set already, return none. No, 1 is not in the set. We then just add root.value, which we just did, 8. Okay, so 8 root.right equals self.correct binary tree root.right. Okay, root.right is then we're going to recursively do the same thing, but for the right node and the left node. So now we're at 3 here on the left and 1 on the right. Okay, same thing. Is 1 equal to none? It's not. So is root.right and root.right value in the set already? So 4. It's not. Okay, then we just add 1 to the value, or to the set. 1. Same thing for 3. We add it to the set. Meets the same conditions. Next, we point 1 to the left and 1 to the right. And then for 3, there is no right. We just point it to a left. And the same thing. So is 4 equal to none? No, it's not. Is root.right and root.right value already in the set? No, it's not. Okay, we just then add 4. Same thing, 9, add it. Now this part is where it gets interesting. 7 has pointing to the right to 4. This value is already in the set, so we cannot add it to the set already. So we remove this 7 value, return none. So this, if root.right and root.right value in self.scene, we return none. Okay, so 7 is not returned and added to the set. It's just none now. And this also applies for the children, so 2. Now that we've got that part over with, the 4 continues on to the right and the left, so these are just added then to the set as well. Notice that then we were just trying to figure out with the set which nodes would be pointed to again, which would reveal to us the wrong, ill-placed, incorrectly placed node. So we're left with 8, 1, 3, 4, 9, 5, 6. This is our answer for the set. And then when we return root, it will be all of these nodes besides 7 and 2. Okay, hope that makes sense. Let's look at the solution. Okay, to start, we first define our constructor. This will keep track of the scene values, so self.scene equals set. So only those values that have already been visited will be added to the set, and this will check then if we have our incorrect node pointing to the value that's in the set. So then we do our base case. So if root is equal to none, return none. Okay. Next, if root.right exists and root.right.value is in self.scene, so the set, we return none. This just means that we've ran into a node which has already been added to the set. This indicates to us that the node that we're currently at is invalid because it points incorrectly. So we return none. And if these two conditions are not the case, then we simply add the node since it's a good value. So we do self.scene.add root.value. Okay. And then we do the same thing recursively for the rightmost and leftmost nodes. So root and then once we've recursively gone through every single node, we can simply return root. This will be our modified binary tree without the incorrect node pointers and node values. Okay, let's see if this works. It does work. Very nice. So what is the time and space complexity for the solution? Well, the time complexity is O of n, where n is the number of nodes in the binary tree. This is because we are traversing each node once. And the space complexity is O of n. And this is because we are using a set to keep track of the values we have seen. And in the worst case, all the values in the tree are unique, and we need to store all of them in the set. So that's O n space, O n time complexity. That's it for this problem. Thank you for watching.